morning one and all. Today I am going to discuss some preformulation properties, right. I will start with the particle size. Particle size characterized by using these, using these terms: very coarse, coarse, moderately coarse, fine and very fine. Particle size can influence variety of important factors like dissolution, suspendability, uniform distribution, penetrability and lack of grittiness. Out of all these three, dissolution rate, suspendability, uniform distribution is very important in the for the determination. While particle size plays a very important role for the improvement of dissolution. So particle size is characterized using three terms: coarse, very coarse, coarse, moderately coarse. I will tell you what is the difference between very coarse, coarse, moderately coarse, fine and very fine. Particle size influenced by variety of important factors. Dissolution rate. What is meant by dissolution? Conversion of solid phase to the liquid phase. When the particle size will be less, surface area will be more, then dissolution will be more. The amount, the area, the absolute surface area or effective surface area, the area, how much area it is going to be exposed to the dissolution medium, that is plays a very important role for the dissolution process. So suspendability, when the particle size will be optimum in the preparation of coarse dispersions like emulsion suspensions, the particles will be uniformly distributed in the dispersion medium. If the particle size will be more than the required size, the particles will be sediment at the bottom of the container and it leads to formation of hot cake and redispersion is not possible. And uniform distribution, even though the particle will be suspended at the bottom of the container, upon gentle hesitation, if the particles will be uniformly distributed, then you will get the stable emulsion or stable suspension. So particle size plays a very important role for the influence of various properties like dissolution, suspendability, uniform distribution. So I said what are different methods are there to determine the particle size: sieving, microscopy, sedimentation, light energy diffraction and laser holography. Sieving, I said already just now, particles are classified into different types based on the size range: very coarse, coarse, moderately coarse, fine, very fine. What is the difference between very coarse, coarse, moderately coarse, fine and very fine? When all the particles will passes through sieve number 10, then you can that one you can classify it as very coarse, right? And if the particles passes through sieve number 22, that we can be categorized into moderately coarse. If all the particles will be passes through sieve number 85, then we can classify it comes under the fine. If all the particles will passes through sieve number 120, that we can be classified as very fine. So by using sieving method, we can find out the particle size from 50 to 150 micrometers. By using microscopy, we can determine the particle size from 0.2 to 100 micrometers. By using sedimentation rate method, we can find out the particle size from 1 micron to 200 microns. I repeat, particles are classified based on their size ranges, right? Very coarse, coarse, moderately coarse, fine and very fine. All the particles will passes through from sieve number 10, that one we can classify it as coarse. All the particles will be passes through sieve number 22, that we can classify it as moderately coarse. All the particles will be passes through sieve number 85, that we can classify it as fine. All the particles will be passes through 120 sieve, that we can classify it as very fine. So by using sieving method, we can determine the particle size 50 to 150 micrometers. By using Microscopy 0.2 to 100 micrometers we can determine the particle size. By using sedimentation method we can find out the particle size from 1 micron to 200 microns. Particle size analysis is very important, especially for the this particle size is very important for the determination analysis of suspensions, right? Particle size analysis in suspensions, globule size determination, globule size distribution in emulsions, particle size analysis in aerosols. Optimum particle size is very essential for getting the therapeutic activity. So particle size analysis are at most important in analysis of suspensions, globule size distribution in emulsions, and particle size analysis in aerosols. And sedimentation method, that is by using sedimentation rate method we can determine the particle size from 1 micron to 200 microns, right? Sedimentation is very important for the determination of formulation and evaluation of suspensions and emulsions, and determination of molecular weight of polymers. So that is about particle size determinations and how to determine what are the various methods and what are their size ranges and what are their applications. Clear so far? So sedimentation method is useful for the determination and formulation and evaluation of suspensions and emulsions, determination of molecular weight of polymers. Next comes to the powder flow properties. Powder flow properties can be affected by change in particle size, shape and density. Please, powder flow properties can be affected by change in the particle size and shape and density. The flow properties depends upon the following force of friction, cohesion between one particle to another. The flow properties depends upon the following factors: force of friction and cohesion between one particle to another. Fine particle possesses poor flow by filling wide spaces between larger particles, causing packing and densification of particles. By using glide end we can alter the flow properties. If there will be the friction will be more between the particles cannot be flow uniformly. So in order to avoid this friction we are adding glide ends, example talc, so that the glide end will be helpful to reduce the friction between the particles, so the particles will be flow uniformly. Yes, I said already the flow properties depends upon the following factors like force of friction. If the friction will be more, between the particles friction will be more, particles cannot be particles flow cannot be proper. To overcome this friction we are adding glide ends. The glide ends will be helpful to reduce the friction between the particles and the cohesion between one particle to another, right? Fine particle possesses poor flow by filling wide spaces between larger particles, causing packing and densification of particles. By using glide end we can alter the flow properties, example talc. So these are the by using this angle of repose, determination of flow property that can be determined by using angle of repose. The maximum possible angle between the surface of the pile of the powder and that is called as angle of repose. Angle of repose can be calculated by the formula tan theta is equal to h by r, theta is equal to tan inverse h by r, theta is equal to angle of repose, h is equal to height of the pile and r is equal to radius. The maximum angle possible between the surface of pile of the powder and the, so that can be calculated by tan theta is equal to h by r, theta is equal to angle of repose, h is equal to height of pile, r is equal to radius. If the angle of repose value will be more, automatically we can get the poor flow, right? A greater angle of repose indicate poor flow, it should be less than 30, right? So the flow property should be excellent, right? So these are various angle of repose values and the type of flow. If the angle of repose value less than 25, type of flow excellent. Angle of repose value between 25 to 30 good. Angle of repose value between 30 to 40 passable. More than 40 very poor. More than 40 very poor. I repeat, angle of repose can be determined by using the formula tan theta is equal to h by r, theta is equal to tan inverse h by r, where theta angle of repose, h height of pile, or radius, or radius. So static methods to determine angle of repose, funnel method widely used, right. There are the number of methods are there. Widely used accepted method is fixed funnel method that we are using day to day in our lab also. Static angle of repose, fixed funnel method, fixed cone method, or kinetic or dynamic method, or rotating cylinder method, and tilting box method. Fixed funnel method, fixed cone method, kinetic or dynamic method, rotating cylinder method, tilting box method. Out of all this method, we are most widely used method is fixed funnel method, right. Fixed funnel method. So we have fixed the distance, take this stand and we are going to fix this funnel and certain height. From that we are going to pour this powder, and when the powder will be touches the pile, we can stop the flowing passing this powders, and we can calculate the radius, diameter first and followed by radius. From that we can calculate the theta. Theta is equal to tan theta is equal to h by r, theta is equal to tan inverse h by r. So this is a method, right. So fixed funnel method, fixed cone method, kinetic or dynamic method, rotating cylinder method, tilting box method. So angle of repose that can be determined by fixed funnel method. Next, measurement of free flowing powder by compressibility, also known as Cars index. Compressibility are also known as Cars index. Formula: Cars index is equal to tap density minus pore density into 100. What is meant by tap density? Repeat, other name for the compressibility index is Cars index. Cars index is equal to tap density minus pore density into 100. So tap density means it is very simple, fast and popular method of predicting powder. It is simple, fast and popular method of predicting powder flow characteristics. So this is the values of Cars index: tap density minus bulk density by tap density minus pore density into 100, right. So pore density, just take the funnel, pour this powder, how much volume it is occupied, and again we will go for tapping, and again how much, again you can calculate how much volume it is going to occupy. Finally we are going to calculate this Cars index: tap density minus bulk density minus tap density minus pore density into 100, per tap density minus pore density into 100. These are the values of Cars index: tap density minus pore density into 100. Tap density I already said, take the funnel, pour this powder, and we can measure this how much volume it is occupied, that is called as, without tapping, that is called nothing but pore density. And again you can go for tapping, again we are going to calculate tap density, and finally we are calculating the Cars index. The formula used to calculate for the tap density for the Cars index is tap density minus bulk density by tap into 100. So these are the values of how you calculate, how you done the values, how you are giving the values for angle of repose. Like that same values will be given for the Cars index. Based on that we are going to decide that whether our flow is good, excellent, fair, poor, very poor, right. If the Cars index value is between 5 to 15, type of flow will be excellent. If the Cars index value between 12 to 16, good. If the Cars index value between 18 to 21, fair. If the Cars index value between 23 to 35, poor. If the Cars index value between 33 to 38, very poor. If the Cars index value more than 40, extremely poor, So angle of repose value less than 30 degrees, very good flow. Like Cars index between 5 to 50, the Cars index value between 5 to 15, type of flow will be excellent. Next, solubility analysis. The solubility of every new drug must be determined as a function of pH over the physiological pH range 1 to 8. So we need to determine the solubility of the drug at different pHs starting from 1 to 8. The solubility of every new drug must be determined as a function of pH over the physiological pH range 1 to 8, because across the GIT we may not having same pH. From starting from stomach to the intestine, the drug is going to be experiences various different pH climatic conditions. That is the reason we are going to check the solubility of the pH, solubility of the drug at different pHs from 1 to 8. And the pre-formulation solubility studies include pKa determination, pH solubility profile, temperature dependence, solubility products, solubilization mechanisms, and rate of dissolutions. Pre-formulation solubility studies include pKa determination, pH solubility profile, temperature dependence, solubility products, solubilization mechanisms, and rate of dissolution. So determination of solubility, accurately qualitative determination. Take the excess drug powder, right? Let us say 150 mg per ml. Add solvent, right? Take this ampular vial minimum of 2 to 5 ml you can take, and shaking at constant temperature at 25 to 37 degrees, 25 or 37 degrees, and temperature to 2 to 8 degrees. Shake for 48 hours, right? By using membrane filter, we are going to filter this solution. The membrane filter size 0.45 micrometers. Determine the drug concentration in the filtrate, and followed 72 hours. Again, we will go for shaking another 72 hours. Again, go for filtration, membrane filter by using 0.45 micrometers. Again, determine the drug concentration in the filtrate. Same concentration determine again. Still the drug is not dissolved. Again, we will go for this shaking, and finally we are going to filter this by using membrane filter at 0.45 micrometers and find out determine the drug concentration in the filtrate. Understand? So take first, while determining the solubility, we are going to take the excess powder drug. Let us say 15% plus solvent. In the ampule or vial, we are going to take just 2 to 5 ml. Shake at constant temperature from 25 or 37 degrees at 2 to 8 degrees. Shake for 48 hours. Go for filtration by using membrane filters and determine the drug concentration in the filtrate. Still undissolved particles are present. Again, shaking will be continued for up to 72 hours by using membrane filters. Determine the drug concentration in the filtrate. Still the drug is not dissolved. If the drug is dissolved, enough. If the drug you can find out this drug concentration. Still the drug is not dissolved, any undissolved particles will be present. Again, go for filtration by using membrane filters 0.45 micrometers, and finally determine the drug concentration in the filtrate. So determination of solubility, semi-quantitative determination. Take the solvent, fixed volume, shaking vigorously, and examine physically just by seeing this, and if any undissolved solute particles will be no means no problem, you can estimate the solubility. If yes means you can calculate total amount added up, adding solute in small incremental amounts. Next one, drug pK and ionization at physiological pH. pK is nothing but dissociation constant of a drug. Every drug will having its own pKa. The pKa determines the extent the drug go for the ionization. Whether it is going to be ionized, the drug species will be present ionized or unionized. pK is nothing but dissociation constant of a drug. The non-ionized substances is lipid soluble, thus dissolve lipid material of the membrane and transported by passive diffusion, whereas the ionized substances is lipid insoluble, therefore permeation is low. Right, pK is nothing but dissociation constant of the drug. The non-ionized substances is lipid soluble, thus dissolve in lipid material of the membrane and transported by passive diffusion, whereas the ionized substance is lipid insoluble, therefore permeation is low. So finally, which species will be crosses biological membrane very easily, ionized or non-ionized? A non-ionized species. Why? Because non-ionized species is lipid soluble, that is going to be dissolved in lipid material of the membrane and transported by passive diffusion. So ionized species is lipid insoluble, where therefore permeation is slow. The percentage of ionization can be calculated as, for acidic drugs, percentage ionized is equal to 100 by 1 plus antilog pKa minus pH. For basic compounds, percentage ionized is equal to 100 by 1 plus antilog pH minus pKa. So degree of ionization depends upon the pH. I already said for acidic drugs the pKa ranges from 3 to 7.5. For basic drugs pKa ranges from 7 to 11. 7 to 11. Next, pH solubility profile. I already said across the GIT we may not having same pH climatic condition. The drug is going to be experiences and different pHs starting from stomach to the intestine. So we need to check the solubility of the drug in all the pHs, right? So that is called pH solubility profile. Take the drug in excess, powder, excess drug powder, stir in beaker, and so that means we are going to check the solubility of the drug in different pHs. Take the excess drug powder, stir in a beaker with distilled water, continuous stirring of suspension, added acid or base. Finally, we are going to measure the pH of the suspension, and finally we are going to determine the concentration of the drug present in the filtrate, right? Based on this we are going to determine the solubility of the drug in different pHs. I repeat, we are going to take excess drug powder, stir in beaker with distilled water, continuous stirring of suspension, yes, and finally we are going to add acid or base. You can find out determine the pH of the measurement of the pH of the suspension, right? And finally determine after this we are going to determine the concentration of the drug in the filtrate. By using this we can calculate the solubility of the drug. We can find out the solubility of the drug. Next one is common ion effect. What is meant by common ion effect? The shift in equilibrium, please see the board what I written. The shift in equilibrium that occurs because of the addition of an ion already involved in equilibrium. For example, silver chloride, AgCl. Again we are going to add NaCl. Already which ion will be present? Chloride ion. Already if chloride ion present in silver chloride, but again we are adding sodium chloride. Definitely common chloride ion will be present in common, both silver chloride and sodium chloride, so that there will be shift in the equilibrium. That is followed. The shift, please listen, the shift in equilibrium that occurs because of the addition of an ion already involved in equilibrium. The shift in equilibrium that occurs because of the addition of an ion already involved in equilibrium. I repeat the definition: the shift in equilibrium that occurs because of the addition of an ion already involved in the equilibrium. Example, silver chloride and sodium chloride. Next one, effect of temperature. The solubility of solute in a solvent depends on temperature. Temperature will affect the solubility of the solute. Don't think that when the temperature increases always solubility will increases. That is based on the nature of the reaction, endothermic or exothermic. Anyhow, that I am going to explain now. The solubility of a solute in a solvent is depend on temperature, nature of solute and nature of solvent. Heat of solution represents the heat released or absorbed when a mole of solute is dissolved in large quantity of solvent. Heat of solution represents the heat released or absorbed when a mole of solute is dissolved in large quantity of solvent. Most of the substances are endothermic, so absorbing heat in the process of dissolution. Applications: pharmaceutical solutions must be administered at or near room temperature, so it is more important factor for product storage than the formulation. To increase the solubility of sparingly soluble solute, to increase the stability by reducing the moisture content. So I said already, don't always when the temperature increases solubility will be increases. That is depends upon the nature of reaction. Most of the substances are endothermic, absorbing heat in the process of dissolution. Applications: pharmaceutical solutions must be administered at or near room temperature, so it is more important factor for product storage than the formulation. To increase the solubility of sparingly soluble solute. Sparingly soluble drug is not soluble completely in a given solvent, so in order to increase the solubility of sparingly soluble solute, we are increasing the temperature, but temperature will increases, solubility will be increases provided the reaction is endothermic. Heat will be absorbed in the process of dissolution. To increase the stability by reducing the moisture content, moisture content. Solution solubility studies. Solution phase equilibrium with solid phase at a stated temperature and pressure determines the amount of drug dissolved, amount of drug available for absorption. So once the drug is going to be dissolved, the drug is available in solution form, because which form is going readily absorbed into our body is solution form. That is the reason whatever the drug we are going to take by orally, whether it is solid or any other form, finally it has to convert it into solution form. Why? Because most absorbable form is solution form. So now we understand the importance of solubility. That is the reason we are going to check the solubility at different pHs. Finally we are going to estimate this based on this pKa, drugs pKa, and we are going to determine the solubility. Once the solubility is determines the amount of drug dissolved and amount of drug available for absorption. Solution phase equilibrium with the solid phase at the stated temperature and pressure determines the amount of drug dissolved, amount of drug available for absorption. Solubility reduction is carried out in certain conditions, enhancement of chemical stability and taste masking products and production of sustained release products. I repeat, solubility reduction is carried out in certain conditions, enhancement of chemical stability, taste masking products, production of sustained release products, production of sustained release products. So these are the various solubility expressions. Please see description and parts of solvent required for 1 part of solute: very soluble less than 1, freely soluble 1 to 10, soluble 10 to 30, sparingly soluble 30 to 100, slightly soluble 100 to 1000, very slightly soluble 1000 to 10,000, insoluble more than 10,000. I repeat, based on the how many parts of solvent required to dissolve in 1 part of solute, based on this solubility can be defined. Solubility can be classified into very soluble, freely soluble, soluble, sparingly soluble, slightly soluble, very slightly soluble, insoluble. Very soluble means less than 1 part of solvent required for 1 part of solute, freely soluble 1 to 10, soluble 10 to 30, sparingly soluble 30 to 100, slightly soluble 100 to 1000, very slightly soluble 1000 to 10,000, insoluble more than 10,000. The equilibrium solubility is based on the phase solubility technique proposed by Higuchi and Connors. The equilibrium solubility is based on the phase solubility technique proposed by Higuchi and Connors. Drug dispersed method: drug dispersed in solvent in a closed container. Hesitated, we can go for shaking. Hesitated at a constant temperature using shakers. Samples of the slurries are withdrawn as a function of time, clarified by centrifugation and assayed by HPLC, UV and GC. Solubilization is defined as spontaneous passage of poorly water soluble solute molecules into an aqueous solution of a soap or detergent in which thermodynamically stable solution is formed. It is a process by which apparent solubility of an otherwise sparingly soluble substance is increased by the process of surfactant. If this drug is sparingly soluble, by the addition of surfactant, solubility of the sparingly soluble drug solubility will be increases by the addition of surfactant. When you are going to add surfactant nature is that formation of micelles, right? The concentration at which micelles is formed is called as critical micellar concentration. The process of forming micelles is known as micellization. Typical micelle is spherical in structure, which contains 50 to 100 monomers. Number of monomers to form micelle is called as aggregation number. So the concentration at which micelles is formed as critical micellar concentration. So we are going to add the surfactant above the CMC, then only the surfactant will forms this micelles, and at particular concentration, critical micellar concentration, the drug solubilizes in a given surfactant. So solubility of the sparingly soluble solute will be increases by the addition of the surfactant. So micelles, the mechanism involves the property of a surface active agents to form colloidal aggregates known as micelles. When surfactants are added to the liquid at low concentration, they tend to orient at the air liquid interface. I repeat, micelles, the mechanism involves the property of a surface active agents to form colloidal aggregates known as micelles. When surfactants are added to the liquid at low concentration, they tend to orient at the air liquid interface.